What's poppin', guys? Welcome to another related rates video. Today we're going to take a look at two different examples. I'm going to work this one out about the spherical balloon, and then I'm going to talk about the soda can problem. So a spherical balloon's volume is increasing at a rate of 314 cubic feet per minute. Find the rate at which the radius is increasing when the radius is 2 feet. So we're going to start this off with what we know, what we want to know, and when we want it. So what we know is that the volume is changing at a rate of 314 cubic feet per minute. What we want to know is the rate at which the radius is increasing, so we want to know dr dt, and we want to know that information when the radius is 2 feet. So the equation that I'm going to use to relate all of this information is the volume equation for a sphere, and if I differentiate both sides, I end up getting dv dt is equal to 4/3 pi as a constant, so I'm keeping that out front, multiplied by 3r squared dr dt, and then I can simplify that equation. So dv dt is going to simplify to 4 pi r squared dr dt. Think about where you've seen that 4 pi r squared before. Now I can do a quick substitution, so I'm going to plug in my 314 for dv dt, and dr dt is our unknown that we're solving for. We know that the radius is 2 feet at this moment, and now I have everything in terms of just one variable, so I can go ahead and solve for dr dt. One thing that I do want to take note of, you'll notice that in the problem that I posted for you guys, that the volume's rate of increase includes pi in it. So that just means that at this final step, when I have 314 over 16 pi, yours is going to include a pi in the numerator so that the pi's will cancel out. It basically makes it a little bit nicer for you. So I roughly get 6.25 feet per second. That is how fast the radius is changing. So now let's take a look at the soda can problem. So the soda can problem that you guys see on your assignment says that a soda can is leaking at a certain rate. That rate is dv dt. That is the change in volume over time. Remember that if the volume is increasing, it's positive. If the volume is decreasing, then dv dt should be negative. Thinking about our soda can, the soda can has a certain radius, and it has a certain height. But when we think about the radius and we think about the height, we have to think about the liquid that's actually in the can. That liquid is at a certain level, and that height is decreasing as the soda leaks out of the can. So the height really represents the height of the liquid, and dh dt represents the changing height of the liquid, which should be decreasing in this context, which means dh dt should be negative. The key to solving this problem is focusing back on the radius. Think about the radius of the liquid. Sure, the can has a certain radius, and that radius represents how the liquid is spread, within the can. But what is dr dt? What is the change in the radius? As that liquid drips out of the soda can, how is the radius changing? Is it changing? Figuring out what dr dt is will help you solve this problem. So this is a more challenging related rates problem, and I really want you guys to give it a good try on your own, submit your work, and as always, I'll give you some advice, some feedback, and we'll work towards getting this one. Good luck.